All right, this video is on chemical kinetics part 3. We pick up where we left off in part 2. Part 2, we finished first order reactions, looking at the line equation and algebraic equation. Today we're going to start with looking at second order reactions. What does the algebraic equation look like, and what does the plot look like? The plot's important because a lot of times when you collect data, you will make a plot, and when you'll try using a line equation, and you'll see a different line equation for the second order reaction, and then based on the line equation, you'll determine what the order of the reaction is. So it's important that you can plot the data and that you can recognize the order of the reaction by the plot of the data. I'm stressing that because I find most students do fine with the algebraic manipulation of the equation to solve for an answer, but they struggle a little bit with the taking the data, plotting it, and then from the plot determine the order of the reaction. So second order reaction means that the concentration of one or more reactants raised to the second power. And later we'll talk about what that means mechanistically in a reaction. But for right now, we'll just think about, for making it simple, what we'll do is we'll just talk about, again, reactant A going to a product. And instead of being first order with respect to A, it is second order with respect to A. So we're going to see a little bit of a difference here. Let me get back to that slide. So looks the same starting out here. You have A going to product, and the rate would be equal to negative the change in concentration of A over change in time. And so the rate would equal K, the rate constant, times the concentration of A in molarity units raised to the second power. And we're going to set these two things equal to each other. And we take, if you've had the calculus, you take the integral of both sides, and you will get this equation here. And it'll be 1 over A at time t equals KT. Notice the difference here. In the first order, this is a negative KT. And then the y-intercept is 1 over A naught, the original concentration. So this looks different than the first order. And this is the line equation. And so if you plot 1 over A versus time, so this is the y-axis, and this is the x-axis. All right, that's what we have here. Then what would you get? Tell me what type of, if I plotted, this is what's important. If I plotted 1 over A versus time, tell me what that plot would look like. And if you can do that, then you understand this equation. If you can't, you need to think about it. So you should get a straight line with a positive slope. You go, how do you know it's a positive slope? Because K here is the slope, and that's M. And it's a positive value. So that's one of the things that's going to tell you the difference between the first order and second order reaction. If you get a positive slope, you know it's not first order. The other thing is where time equals 0, that's your y-intercept. So that would be here. So that's easily defined. That's easy to find as well. So just keep that in mind. I want you to be able to do this algebraically, but also by plotting or graphing data. Let's see here. So that's what they're showing here. Now, again, I want to point out that the if you just plot concentration versus time, it's going to look, I mean, you can't tell really looking at this if this is first order or second order. We see that the concentration is going to decrease over time. We know it's faster initially than it is down in this region. And so it's really hard to tell without any comparison that this is second order. It is only when we plot 1 over A versus T and we get a positive slope line that we know that it's second order. All right, so let's solve for the half-life. So we're going to have a half-life for this as well. And so what we do here is, this is the important part, is that the concentration at time would be equal 1/2 the original concentration. Okay, so they put that, they substitute in for concentration at time 1/2 the original concentration. So if you want to think of this, this is 2 over A naught. The 2 goes in the quotient of a quotient, so it's 2 over A naught. And so if you take 2 over A naught and you subtract 1 over A naught from both sides, subtract 1 over A naught from both sides, then you're going to get 1 over, well, let's do another step here. So then what you'd have is KT 1/2 equals 1 over A naught, since 2 over A naught minus 1 over A naught is 1 over A naught. And then we divide both sides by K, and we get this equation here. So you need to memorize that equation, and you're going to use this equation to determine half-life, or given the half-life, determine the original concentration. What I want you to know about second order half-lives is the half-life is dependent upon the initial concentration. We wish nuclear waste would be this, because we'd pile it all up in one place. You'd have a high initial concentration. The higher the initial concentration, the lower the half-life. So it's an inverse relationship there. So that's what we would like ideally, but nuclear reactions are first order reactions, or nuclear decay, let's at least say that. All right, so let's look at a problem. Let's look. So we have monoatomic iodine reacting with itself, and so that's what we see here is monoatomic iodine reacting with itself. Okay, so here we form diatomic iodine. This equation can also be written this way. Okay. Says the reaction, they tell you it's second order, all right? And they tell you what the rate constant is. Now, here's the thing to remember. The rate constant tells you that it's second order. All right? So remember those. Like first order, the rate constant will be seconds to the -1 power. So if you see 1 over molarity units seconds, that's what this is saying. That's going to indicate it's second order. All right, it says the initial concentration of the iodine, monoatomic iodine, is 0.086 molar. Calculate the concentration after 2 minutes. And part B says calculate the half-life of the reaction when the initial concentration of iodine is 0.60 molar and when the initial concentration is 0.42 molar. All right, so the first thing we're going to look at is the time. So the time is 2 minutes, and we know that there's 60 seconds to a minute, and you go, well, why do we have to do this? Well, the reason why we have to do this is that we know the rate constant is in molarity units seconds. So therefore, we have to convert the minutes to seconds. We know this is, you're going to memorize this, the second order equation. Okay. We know that the K, the rate constant, is this, times the time that we just calculated here, and then 1 over the initial concentration. And that gives us this number here. I don't know how many times I see students stop right there and say, that's my answer. Well, first of all, it's not the answer. If you're watching your units, and I can't stress this enough, this is in 1 over molarity units. You want molarity, not 1 over molarity units. The other thing is, if you recognize this part here, that's what you just solved for, not this. So to get this, you have to do the reciprocal. So you say 1 over. 8.4 times 10 to the 11th 1 over molarity unit. So if you don't like this, just exit out and put a 1 over m here like this. And then you can see that this is in the quotient of a quotient, which is the same thing as being in the numerator. So the reciprocal of 8.4 times 10 to the 11th will give you 1.2 times 10 to the negative 12th molar. All right. Another thing would tell you that you've made a mistake is that if the initial concentration is this, there's no way you're going to get a concentration that much greater, right? It should decrease. The concentration of the reactant should decrease if you're going from a reactant to products. And so you would expect this number to be less than what you initially started with. So that's a check to say, hey, yeah, I'm on the right track. So bottom line, after 2 minutes, the initial concentration has decreased to 1.2 times 10 to the negative 12th molar. So that's part A. Watch your units. I can't stress that enough in the Chem 180. We're doing a lot of math in this class, and we're using mathematics to describe physical phenomena. And it's important that you watch the units. That'll tell you that you're on the right track. All right, so let's look at the next part, which is the half-life. So the half-life, we have initial concentration is 0.60 molar of the monoatomic iodine. The half-life, you'll memorize this equation here. And it's real easy. You already know what K is. That was given in the problem. They tell you what the initial concentration is. And then we solve for this, and this molarity and that molarity will cancel out. And this 1 seconds to the minus 1, again, that means the same thing as 1 over seconds. So seconds is in the quotient of a quotient, pops up into the numerator. And we get a half-life of 2.4 times 10 to the negative 10th seconds. Now, if we increase the initial concentration or decrease it to 0.42, so we went from 0.6 to 0.42, and the question is, will the half-life increase or decrease? Well, as we decrease this initial concentration, we increase the half-life. It's an inverse relationship. So to prove it, we put in the same rate constant, assuming temperature is not changing through the course of the reaction. We put in our new initial concentration, which is less than this concentration, and notice the time does extend. It takes a longer amount of time for us to reach the half-life. So that's what they're doing. That's why they're doing this problem, is to show you the relationship between initial concentrations and how does that affect the half-life. And again, it's an inverse relationship. Concentration goes down, half-life time goes up. All right, so what I would do is make a note of this slide. This is a slide that has all the information that we've been covering. It gives you the integrated rate law, and then it also gives you the half-life. And so you want to spend some time memorizing this. And the other thing you want to spend time on is, what do the plots like this look? If you're graphing these things, if you're graphing these items, especially these, get these into a line equation. What do the graphs look like? Because that's usually one of the test questions. Is I'll put up some graphs and I'll say which one of these represents a first order, second order, or zero order rate law. So take the time to plot these, or at least look at them up. I mean, you can Google what does a second order rate law plot look like, or first order, zero order. Actually, we've done the first order and second order. You just need to look up the zero order. All right. So very important that you understand not only the algebraic form and how to solve, but also graphic form. All right, so that concludes the section on integrated rate laws, zero, first, and second order, and what their plots look like. Now we're going to talk about temperature dependency. So everything we've done up to this point, we assume the temperature is held constant, And what we've been doing is varying the concentration and seeing how the rate of reaction increases or decreases based on concentration of reactant. So now we're going to focus on the temperature. Well, how does temperature play with kinetics? And so temperature actually changes the rate law, or the rate constant. The rate constant, that's what I want to say. Okay? So think about it. You have a box, and in this box, we'll say you have two particles. What is the chance that that particle and that particle are going to collide? They have motion, they have kinetic energy, and so does their chances of colliding increase or decrease as temperature goes up? So as temperature goes up, what happens to these particles? Well, their kinetic energy goes up. All right, their kinetic energy goes up. They're going to be moving faster in the box, and they're more likely to collide. So this is called collision frequency. So a greater collision frequency leads to a higher reaction rate, which makes sense because once these things collide, they may stick together and form a new product, and they may not. They may bounce off each other. But the rate of the reaction is proportional to the number of collisions per second. All right? The rate of the reaction is proportional to the number of collisions per second. More collisions per second, the more likely you have an effective collision that will create a new substance. So that's the next key term, and that is effective collisions. Effective. So just because two things collide, you guys know this, you've seen things collide before, they slam into each other, and then they just bounce off and go the opposite direction. That's not an effective collision. So not every collision between molecules results in a reaction. The ones that do result in a reaction are called effective collisions. So it says the molecule in motion possesses kinetic energy, and the faster it's moving, the greater the kinetic energy. And then what happens is when these molecules collide, that kinetic energy is turned to vibrational energy. And if the initial kinetic energies are large, then the colliding molecules will vibrate so strongly as to break some of the chemical bonds. And if those bonds are broken and new things are formed, we call that an effective collision. But what I want to stress here is not every collision is effective. So it says if the initial kinetic energies are small, molecules will merely bounce off each other and not interact. They've got to have enough kinetic energy that they can break the bonds, enough vibrational energy is generated to break the bonds and new bonds to be formed. So the minimum amount of energy required to initiate the chemical reaction is called activation energy. You need to know this term. We're going to be working with it quite a bit. And if you don't have this minimum amount of energy, you're definitely going to have an ineffective collision. So let me give you an example. You see this every once in a while this time of year. So you see on the news somebody's house is blown up, and they say, well, they had a gas leak. So why did the house fill up completely with gas before it exploded? So let's talk about what's going on here. For the most part, what we have is natural gas is methane. And methane is a gas. It reacts with oxygen gas. And it forms carbon dioxide and water. Carbon dioxide gas and water. And we'll say it's a liquid here, that's fine. And let's see, is it balanced? I needed 2 here. That gives me a total of 4 oxygen, and I needed 2 here. All right, so there's my balanced chemical equation. So this reaction is explosive. We know this burns in a controlled environment like a gas furnace, it's fine. But what happens when this fills up the house and it's not exploding? Why isn't it exploding? Why doesn't, when the natural gas fills up the house, that it, why didn't it explode when it just filled up the basement or the second floor? Why does it wait until the entire uh, house is filled with gas? Well, let's think about it. And that is going to be based on this activation energy. So let's look at the next slide. So let's look at a collision. They give an example of a collision of nitrosyl chloride with chlorine. So let's look at this closely here. Here's a chlorine atom. That's what this represents. Here's the nitrosyl chloride. Here's a chlorine. Here is a nitrogen. And there's an oxygen. The chlorine slams into the nitrosyl chloride. That's what we have here. That's the collision. And then the chlorine breaks from the nitrosyl chloride, breaks away, and now we have diatomic chlorine, which is its natural state. And the nitric oxide shoots off to the side here. That's effective collision. That's an effective collision. That's a chemical reaction. We have new products being formed here. But we could also have this happen. The chlorine monatomic atom does not have enough kinetic energy that when it collides, or it's the orientation in this case, if the chlorine collides with the oxygen, nothing happens. So that's about orientation. And so this is an ineffective collision. So that's what they're saying. In collision theory, an effective collision not only has to have the kinetic energy, it has to be oriented in a way that favors the reaction. So the next slide shows us this activation energy. And it also illustrates what's going on here. So here's our reactants. Here's our products. We don't go directly from reactant to product like that. If we did, then it would happen instantaneously. It wouldn't be like the house filling up with gas, and as soon as some gas was released, it would explode, and it would be a much smaller explosion than blowing the whole house up, right? But here's what's going on. It doesn't go this way. There is, from where the reactant energy is to the top of this peak, is called activation energy. And what's happening is you're somewhere between the reactants being separate and the products here. And this is called an activated complex. Activated complex. It's when the chlorine initially collides with the other chlorine. Notice it hasn't broke off. And so we were not at the product stage yet, but we're not at the reactant stage either. And it always takes energy to go from the reactants to this activated complex. And you say, why does it always take energy? Well, you have to have kinetic energy for this to slam together, and you have to have the proper orientation of the molecule for this to happen. So both orientation and kinetic energy are required for this to be an effective collision. So the top up here is called the transition state. This substance is called an activated complex. And from the energy of the reactants to the top of the peak is called the activation energy. You say, well, what's the activation energy when the house blows up? Well, usually if you listen to these news reports, it can be, if the homeowner's not there, it's usually like maybe the thermostat kicks on, and a little spark from the thermostat is enough activated energy to cause the reaction to happen. It can be when the homeowner gets home and they open the door and they drag their feet on the carpet or something and create a little bit of static electricity, and that one little spark is all it needs for it to be ignited. So that's the thing about activation energy. You can have a room full of hydrogen gas reacting with oxygen gas, and it'll form water, and this is an explosive reaction, but it's not going to happen until we overcome the activation energy for these bonds to break, these new bonds to form, and there'll be some kind of activated complex to get from here to here. So that's what we're looking at. That's what we're focusing on. So this is called Arrhenius Equation. You'll need to memorize it. You're going to memorize these equations because you're going to be doing so many problems. But here we have the rate constant is equal to a collision frequency factor. That's usually given in Chem 180. We don't generally ask you to solve for that. And then here's the part that students have the most trouble with, and that is right here. So we're using the inverse natural log E. We have negative the activation energy here, negative the activation energy, divided by RT. Now we know R, but the R we're going to use here is not the 0.808206. We're talking about energy, so we're going to be using this R, and you'll need to memorize that. That the gas constant that we're going to be using to talk about Arrhenius' equation is joules per Kelvin mole, not liter atmospheres mole Kelvin. T is the absolute temperature, just like before, and so that's what we're looking at. Again, A is the collision frequency factor. It's treated as a constant given for a given reaction over its reasonably wide temperature range. So know this equation, and then here's the thing I want you to do before you go to the next slide. Break that down into a line equation. So you know a line equation is y equals mx plus b. We just saw it in the last section. I want you to convert this algebraic equation into a line equation. See if you can do that. All right, here we go. So the inverse of the natural log is the inverse of E. The natural log is the inverse of E. So here's what we have. We take the ln of both sides, and what we get here is ln of k, ln of a, the collision frequency factor, and now the ln of, and then E. Those are the inverse, and we get that brings what's in the exponent to the base, and we get negative E sub a over RT. All right, so then you got to manipulate it. This ln of a, that's going to be your y-intercept. And 1 over t, the temperature is going to be the x-axis, and ln of k is going to be the y-axis. The slope, when you plot this, again, what would this plot look like? So I expect you to be able to say, okay, I know what this would look like. I want to draw a y-axis. I want to draw an x-axis. Y is ln of k. X is 1 over t. Again, right there. Right there. And because this is negative, I know the slope is negative, like so. And when the temperature is 0, 1 over the temperature 0, well, that'd be undefined, but close to that, we will get the y-intercept, which is ln of a. So, memorize the line equation. You got this one to memorize, and then you can either manipulate it or you can memorize the line equation. All right, so another problem, more data, and again, I'm hoping you're getting some of this in your lab, because this is kind of stuff you do in the lab. All right, so watch what happens here. You have a reaction. Carbon monoxide reacts with nitrous oxide to form carbon dioxide and nitric oxide. And so here we have a plot at 4 different temperatures, or we have data at 4 different temperatures. So we're not varying the concentration. We are just varying the temperature and seeing what happens to the rate constant. And yes, the rate constant changes. As the temperature goes up, the rate constant goes up as well. So you're going to take this data, and you know that it's second order. You can tell that this one's second order because of the rate constant. And so we're going to plot the ln of k. Remember what we have to do here. We have to know the line equation. That it's the ln of k equals negative e sub a over r 1 over t plus the ln of the concentration of A. So I need to plot ln of k versus 1 over t in Kelvin, and that will allow me to draw a line on this plot. So let's do that. So the first thing they do is actually just change the k's to ln of k's, and then they change the temperatures to 1 over k. So you can do that if you want to. And so then when they plot the data, they get a negative slope line, which it should be. And then what's so cool about once you get the line, you can take 2 points on here, and that's what they do here. They take from here and they go down here, and then they take the line this way like that, and they go from here to here, and they get the rise over the run, the change in y over the change in x, and they get that for the slope. And when they solve for the slope, they get that value there. Remember, this is in the quotient of a quotient, so it pops up into the numerator, and so we get that value there. What is that value? Well, that value is negative E sub A over R. Now, a lot of people think that that's the activation energy. It's not. It's equal to negative E sub A over R. And again, why do you know this? Because it's ln of k equals negative E sub A over R 1 over t plus the ln of A. All right, so we're not done yet. And that a lot of times is a multiple choice answer to see, are you following what you're doing? So just be careful with that. Now, we know that if we're going to solve for E sub A, the activation energy, we need to divide the number by negative 1, and we need to multiply by R, the 8.314 joules per mole Kelvin. So that's what we're doing here. We solve for the slope. We're going to multiply it by negative 1, and we're going to multiply it by R to solve for E. And again, what we're doing here, negative E sub A over R equals the slope, and we're solving for E sub A. Now, if you're watching this carefully, the Kelvin cancel out, and we're left with joules per mole, and most of the time, the question will ask you for the answer in kilojoules per mole. So again, watch your units carefully. When you solve this, you get joules per mole, but because most things on the human scale are in kilojoules per mole, a lot of times they'll ask for the answer in kilojoules per mole. So just be careful with that. Again, it's terrible to see a student go through the entire problem, get all the way to here and say, oh, all right, here's my answer, and it's actually they're asking for it in kilojoules per mole. So just be careful there. That's the thing about 180. It's about being meticulous in your work, writing down step by step so anyone can follow it, and you can follow it, and you can watch your units cancel. All right, so then the next question is, that's fine and good what we've been doing, but what I want to know is, how much does the rate of reaction change as I increase or decrease the temperature? I want to compare two different temperatures and know how much faster the reaction is. All right? So what we do here is we have two Arrhenius line equations at different temperatures. We're going to combine these two, and I want to look at the difference in these temperatures. Like, what's the difference in the rate at these two temperatures, right? So I'm going to combine these equations together. And when I do that, I get the ln of K1 minus K2. And then I get the ln of A minus E sub A over RT, 1 minus ln of A E sub A RT2. We're just combining these two equations together. And then if you want some practice with your math, you can manipulate these to this equation. So those of you who want to practice your math, you can manipulate. You can factor out factor out the E sub A over R, because that is a constant, right? The gas constant's not going to change. The activation energy is not going to change. The ln of A's, they subtract out. And so then we have the factors that are, the variables here is 1 over T1 plus 1 over T2. So what they did is it's minus a minus. And so we get minus 1 over T1 plus 1 over T2. But people don't like this because you miss this negative sign right here. And so they flip it and make it 1 over T2 minus 1 over T1. All right? So that's fine. This is what we like the best. This makes it, you can do it this way. It's just that you got to make sure you got the negative with the T1 here. And a lot of students miss that. So this is the equation I would memorize. If you want to compare the rates of reaction or the rate constants at two different temperatures, that's the equation we're going to use. All right, so here's a problem. Here's an example of how you're going to do this. So it says the rate constant for a particular first order reaction, and we know it's first order. They don't have to tell us that. When we see a K of seconds to the negative 1 power, we know it's first order. At 3 different temperatures, 1, 2, 3, and we see that the rate increases, or the rate constant, which is also the rate, right? Okay, so we have the ln of K1 over K2 equals E sub A over R, 1 over T2 minus 1 over T1. There's our equation that we have to use. It's a plug and chug problem then, right? So they want to know, using the data, calculate the activation energy. So we could choose either one of these data. We could choose the first and second or the first and third. It's up to you what you want to do here. So they manipulate the equation to solve for E sub A over R. So again, they divide both sides by, they multiply both sides by R, and then they divide by 1 over T2 minus 1 over T1. Again, this is where the math really comes into play here. You have to be able to manipulate the equations to get what you're solving for, and that takes time. It's not something you rush. But once you have this solved, now it's just plug and chug. You put in the information that was given in the on the last page, making sure you're writing your units down so you can see what happens here. So the seconds cancel out here, and that's a unitless number. And then this is going to come out in Kelvin, right? Because this Kelvin's in the quotient of a quotient. And just be careful here. Just say 450, hit the x to the minus 1 key on your calculator, and then say subtract, and then hit 400, x to the minus 1 key. This is where I see students make the most mistakes, is right here, and subtracting those two. So if you do it correctly, you should get this number here. And again, what's the units? Well, it's going to be joules per mole, because that Kelvin's going to cancel out with these Kelvin when we manipulate it. And then again, that's not acceptable. We generally want the final answer in kilojoules per mole. So 91,173 joules per mole is 91 kilojoules per mole. All right, and you can do that. Divide by 1,000, and you get 1,000 joules equals a kilojoule. There you go. And we calculate the activation energy. Now, if you want to try one of the other experiments, you want to compare another two, you can do that, and you should come up with the same answer to prove that the activation energy does not change through the course of the reaction. All right, and so then we have another problem. So in this problem, they tell you it's first order. They tell you what the activation energy is. So they tell you what the activation energy is, and they tell you that the rate constant for this reaction at 150 degrees Celsius is this, and they want to know what the rate constant is at 300 degrees Celsius. So again, we're using the same equation. What we're trying to solve for is K2, the rate constant at the higher temperature. They manipulate the equation and you get this equation. This is what takes the most time right here, and you got to be meticulous about it. All right. The next thing, so let's say you get this part right. The most common mistakes, if you get the equation right, is not for converting these degrees Celsius to Kelvin. You have to do that. And not converting the 83 kilojoules per mole, converting that to joules per mole, because that's what your E sub A is. So you can either convert the activation energy into kilojoules per mole, or you're going to convert the activation energy in joules per mole, just to make it work out with R. That's what we're doing, right? This is 8.314 joules per Kelvin mole, and if you keep this in kilojoules per mole, you're not going to get the correct answer. So let's look at the next slide. So here we go. Let's look at it closely. So if you look at this slide, like I said, we've converted the temperatures into Kelvin. So you see that here. And they converted the 83 kilojoules per mole into joules per mole here. So that joule and that joule cancel out. And that mole cancel out. And then those kelvins and these kelvins will cancel out. And so you'll be left with a number over seconds to the -1. And if you solve this correctly, you should get that answer there. All right. And I don't care if you write it this way. That's probably the best way to write it. But if you want to write it 10 with the decimal here, you can do that as well to show two significant figures. But that's the rate constant, 300 degrees Celsius. Now, what I would do before I'd say that's my final answer, just compare this lower temperature to the higher temperature. You would expect the rate constant to go up if you increase the temperature. And it does. It goes from 2.1 times 10 to the negative 2 to 10 seconds, 10 over seconds. Okay. All right, that's where we're going to stop at today. This is part 3 of chemical kinetics. The next lecture will be on reaction mechanisms and catalysts, and that'll finish chapter 14 in the McGraw-Hill book, and we'll move on. And then we'll move on from there.